Welcome back to the second season of Crystal Clear Electronics. This is the last video of chapter 23, where we will make a brightness sensor software.
The goal now is to create a program that stores data from the brightness sensor on our development panel, and it stores a timestamp every half second on the SD card. All this in a way that we can easily view and interpret the data on a computer.
Let's make a more precise specification for the functional description. The first thought might be that we need some way to stop data collection and writing to the SD card. Otherwise, we cannot remove the SD card without risking damage to the file system. To start and stop the measurement, we use, let's say, a push button and a state machine in the software.
Which timestamp should we use? It is advisable to choose a simple one first. You can modify it later. The simplest is to use the timestamp of the HAL-GET-TICK function. Of course, this only shows how many milliseconds have elapsed since the microcontroller was restarted, not an absolute time and date value.
What file format should we use? It is advisable to choose the CSV format, which stands for comma-separated values. This is actually a text file representing a table. A row in the table is made up of the individual rows in the text file, and the columns are made up of the comma-separated values. Usually the first row contains a header, so in our case, we should see something like this in the file. The file name should be, say, data.csv. The advantage of this format is that it can be handled by many computer software, for example all spreadsheets or mathematical softwares.
So, to summarize, we need to create a software that works like this. In the default state, LED 1 is lit, and we wait for BTN3 to be pressed. Once this happens, we start the measurement, meaning we open the data.csv file in append mode. If it does not already exist, we create it and include the header in the file. In the measurement status, we retrieve the luminosity and timestamp every half second and write them to our CSV file. We also toggle the state of LED 1, so it will flash to indicate to the user that the program and measurement are running. When we press button 3, we close our file and return to the default state. In the error state, LED 4 should flash with a period of 200 milliseconds. Press BTN3 to acknowledge the error and return to the default state. In case of any serious error event, this error state must be entered.
We have now also created a framework software called Lecture 23 Data Logger, which is based on the project used to demonstrate FAT-FS. The difference is in the I2C interface of the brightness sensor and the use of the push button. Now we have to work in the files datalogger.c and datalogger.h. The parts to be implemented are marked with to-do comments. In the btnhandler.c and btnhandler.h files, there is little task that performs the debugging of the push button. To use it, just call the button is rising edge detected function, which returns true if a new rising edge, a button press, has occurred. The data logger task and button task have already been created in the source files, and they start automatically when FreeRTOS starts.
You may want to start by formatting the SD card as you did in the previous software, so that you can be sure that the file system is set up correctly. Then, I will ask my colleague beside me to insert the SD card into the slot on the development panel and connect the power supply. Until you do this, I will turn on the camera, not forgetting this time, so we can show a better picture from above the panel to our viewers to see what we do. Immediately, you can see that as soon as we plugged in the USB cable and powered our panel, LED 1 lit up, indicating that we were in the default state. In principle, if I now press the button, this LED will start flashing, indicating that we are in measurement mode. Now just for fun, I'll put my finger on the light sensor, take it off, put it on again, and take it off again to see if there's any change in the data. And finally, I stop the measurement by pressing the button. LED 1 stops flashing, so we're back to the default state. If you're not experiencing this, or at least not this functionality, then there is probably something wrong with your software. To try to find the bug, use the debugger as we did earlier in the curriculum. If this fails, then an implementation of the software can be found as Lecture 23 data logger example on our website. After downloading, you can use it freely.
If you haven't done it yet, stop the measurement, remove the power, and insert the memory card back to the card reader. After this, the data.csv file should be on it, and if you open it with the text editor, it should contain the measured data in CSV format. This looks something like this after a short measurement.
In a real environment, the tick-based timestamp is not very good because it only tells you how much time has passed since the microcontroller was restarted, so the file contents are not an absolute time. Fortunately, we have already used RTC in a previous chapter, so we can also use it to generate a timestamp.
The project can work with more than just a brightness sensor. We have already seen temperature and humidity sensors in other topics, so implementing them should not be a problem. Of these, you can connect as many as you'd like, even different sensors as well to your microcontroller, so you can record their data too.
If we need to collect measurement data frequently, or for a long time, the capacity of the SD card may limit the length of the measurement. In such a case, it is worth thinking about how to store data in a space-saving way. The CSV format is convenient and easy for the human eye to understand, but it is also very wasteful. Consider, for example, that the number 1,002,300 is represented in 7 characters, or 7 bytes, whereas in binary, it fits into a 32-bit number, or only 4 bytes. Not to mention the comma and new line characters, which waste additional space. In such cases, it makes sense to store the data in binary, for example 4 bytes of timestamp, 4 bytes of luminance, resulting in a significantly smaller file size. Of course, we cannot interpret this file by opening it with a text editor, but we need to create some software on our computer that converts the binary data to something that us humans can also read.
In this chapter, we learned about the history of data storage devices, and then in more detail about the external and internal structure of the SD card. We looked at the functions needed to manage FAT/FS and tried them out in various applications.
I trust that by now, no one will have any doubts when it comes to data storage in an embedded system. I hope that when you come across an SD card on the shelves of an electronics shop, you'll feel good knowing what's underneath the plastic case.
The next and last chapter is the finale of the Crystal Clear Electronics 2 video series. In the last video, we will create a complex application, in which we will apply most of the knowledge we have gained. So be sure to follow us and don't miss on the last videos. Bye!
Bye!